Hello learners, welcome to this course on practical machine learning using Google Colab. So in this video tutorial, we will be discussing about fundamentals of computer vision part 4. The topics which we cover in this tutorial are morphological operations, using structuring elements, how to create an structuring element and how to use this structuring element for different morphological operations we will be discussing in this lecture. So some of the operations are erosion. So erosion is nothing but removing the outline of an object, or we can say in other words it is something like thinning the size of an object. Second operation which we are going to discuss is dilation. So dilation is something like thickening the outline of an object, thereby there is an increase in size of the object. Opening is providing a separation between two objects or inducing some space between two characters or an object. Closing is just the opposite of your opening. So here we try to form a little bit, the gap between the two objects can be little bit reduced by using this closing operation. Morphological gradient, we try to find the outline of an object. Same way, white hat is something like we can highlight the brighter regions in a darker background that we can able to extract using this white hat or top hat. Whereas in black hat, we will try to extract the darker regions from a brighter background. So these are the operations which we will be discussing in this tutorial. Now let us move on to the Google Colab. So as I said, mostly these morphological operations are nothing but simple transformation. It is applied to binary images or grayscale images. So we normally apply this morphological operations to binary images. So by doing so, we can either increase the size of the object, or we can decrease the size of the object, or we can induce some space between the objects, or we can reduce the space between the objects. We can also find the outline of the objects using this morphological operation. So in order to perform a morphological operation, we need to define a structuring element. So we can think of the structuring element as a kernel or a mask, which is applied onto an image. So we already studied about a mask. A mask is something like which we can apply to an image, thereby we can extract a particular region from the original image. So whereas there is another type of small matrix called as kernel, which can be used for extracting the features from the image. So here we can think of the structuring element also in that similar terms with respect to your kernel or a mask. But in a kernel, we will be applying a convolution operation, whereas for a mask, we will be using a bitwise AND operation on an image. But here, by using the structuring element, we will do some simple pixel test. Based upon the test result, we will try to arrive at some solutions. So that is what we try to do in your structuring element. And as usual, when I use a kernel or a mask, we try to run this kernel or a mask from left to right and from top to bottom for each pixel in an image. Same way here also we are going to run the structuring element from left to right and top to bottom for each pixel in an image. So let us take an example of a structuring element. It can be a 4 neighborhood or it can be a 8 neighborhood structuring element. So 4 neighborhood means I have a center pixel and we have 4 pixels, one around the north direction, south direction, west direction and east direction. Whereas in an 8 neighborhood, we also consider the corner pixels like north, west, northeast, southwest and southeast. So that consists to be a 8 neighborhood. So I will show you how this 8 neighborhood and 4 neighborhood looks like little bit later. So we can also define the structuring element of any arbitrary shape, like any arbitrary rectangle or circular structures. We can define this structuring element. It need not be the 4 neighborhood or the 8 neighborhood, depending upon the application. For example, if I am going to work with some license plate, so license plate usually it will be in a rectangular structure. So in that case, I can use a rectangle type of structuring element to do that operation. So in OpenCV, we have a function called as cv2.get structuring element. So this function can be used to create a structuring element. In NumPy also we have a function to define the structuring element, but for this tutorial I will be using this OpenCV based structuring element creation. So now let us connect this Google Colab to a cloud environment. Just press this connect button. It will get connected to your cloud environment. Once it gets connected, we will start executing our program. So it will get initialized and it will get connected to your cloud environment. Now it is connected. Now let us see the program. So let me zoom in a little bit so that the code will look a little bit better. First thing we are going to do is we are going to import the necessary packages. So as usual, to visualize an image, I am going to use this cv2_imshow function from this Google Colab patches library. We are going to use some computer vision version 2 packages, functions. Same way we are also going to use some NumPy. NumPy is a numerical Python library. In short form, we can define it as NP. So this NumPy is mainly used for matrix as well as array computations. And in order to do some plotting operation, we will be making use of a matplotlib library. In that I have a pyplot. So this pyplot in short form, we are going to use it as PLT in our program. So let us run the cell to see whether any importing errors are there. No. So there are no importing errors. So now let us try to visualize the structuring element. So for that I am going to get an image into our Google Colab environment. So here let me select the file. Select a file, open, then try to visualize the file. You can see this is a 4 neighborhood structuring element and a 8 neighborhood structuring element. So in the 4 neighborhood structuring element, at the center pixel, we have the pixel for which we are going to compute the value, and this value will be computed based upon the 4 neighborhood pixels: north pixel, south pixel, west and east pixel. In case of 8 neighborhood, the center pixel value will be computed based upon the neighborhood, 8 neighborhoods: north, south, west, east and also northwest, northeast, southwest and southeast pixels. So this all 8 pixels will be used for determining the value of the center pixel. Now let us discuss the different applications or usage of this morphological operation. So we have number of operations which can be performed like erosion, dilation, opening, morphological gradient, black hat and white hat. So let us discuss one by one in detail with an application. First let us start with erosion. So erosion, from the name itself we can understand it is going to erode the pixel values. Usually this erosion will happen at the outline of an object. Usually the erosion will happen at the outline of an foreground object. So for example, if I have an object and the outline pixels will get eroded. When it gets eroded means the size of the object gets reduced. So that is what happens in your erosion operation. So this is just like water rushing along a river bank as it erodes the soil. So when the water flows on any river bank, what happens? The soil gets eroded away. Same way, when I perform this erosion operation, what happens? The pixels on the outline of the foreground object will get eroded away. Thereby, the size of the object becomes smaller. So that is what happens in your erosion operation. So the basic logic behind this erosion is, this is the condition. A foreground pixel in an image will be kept only if all pixels inside the structuring element are greater than 0. Otherwise, the pixels are set to 0, which means I have to see the entire neighborhood. If I take a 4 neighborhood function, I have to see the complete neighborhood function. If all my neighborhood has a valid value greater than 0, then only I should keep that pixel. Otherwise, I should discard that pixel. Usually, when we try to apply this logic on an outline of an object, what happens? The sum of the neighborhood may not have a value greater than 0. So thereby the outline of the object will get eroded away. Thereby there is a decrease in size of the object. So it is mainly useful for removing the small blobs in an image. If I have something like a salt and pepper noise is nothing but small white patches on the image. So if I have some small blobs in an image, so those things can be easily removed using this erosion. So we can apply multiple number of times this erosion process, thereby the blobs can be removed in a significant manner. And also it can be used for disconnecting two connected objects. If I have two connected objects, if I try to do erosion, then there will be a separation between the two objects can be visualized. So how to do this erosion operation? We have a very simple function called as cv2.erode, which is used for applying this erosion operation to our image. And the next morphological operation which we are going to discuss is dilation. So which is just an opposite of an erosion. So in erosion, the pixels on the outermost layer of an object gets eroded. Whereas now in dilation, what happens? The pixel on the outermost layer of an object gets thickened. So there is a increase in the size of an object. In the erosion, there is a decrease in size, whereas now in dilation, there is an increase in size. So dilation will grow the foreground pixels. So dilation increases the size of the foreground object and are especially useful for joining the broken parts of an image together. So the logic behind this dilation is, a center pixel P of the structuring element is set to white if any pixel in the structuring element is greater than 0. So we take a pixel value and we try to see its neighborhood. If any one of the neighborhood is having a value greater than 0, then we need to maintain that pixel. Whereas in case of erosion, it is just opposite. We look at the neighborhood. If any one of the pixel value in the neighborhood is not greater than 0, then we will try to discard that pixel. Whereas here we try to retain that pixel. So thereby what happens? The size of the object gets increased. So how to apply this dilation operation? It is very simple. We just use this cv2.dilate function, and it can also be applied multiple number of times. Thereby I can increase the size of the object to a significant size. Next operation which we are going to discuss is opening. So opening is a combination of erosion and dilation operations. And opening is nothing but an erosion followed by a dilation. So first we do erosion of an image, so thereby the outline gets a little bit eroded. If I have some noise, small blobs, it will get lost, and then I try to do dilation, thereby thickening the size of the object. So removing the noise and enhancing the size of the object can be performed using this opening operation. So this is used to remove the small blobs from an image and also to regrow the size of an original object. So that is the advantage of doing your opening operation. Next operation which we are going to discuss is closing operation. So closing is something like opposite of your opening. So here what we do, first we do dilation followed by an erosion. In opening, first we do erosion followed by a dilation, whereas in closing, first we do dilation followed by an erosion. So here by doing this, what happens, the objects can be brought near to each other, or the gap between the two objects can become narrower. So that is what we say it as a closing. So how to do this? We can use this flag cv2.morph close flag to do this operation. Next operation which we are going to discuss is morphological gradient. So gradient is nothing but we try to see the variation of intensity along different directions. So here by using this morphological gradient, I can find the outline of an object. So that is what we try to do in your morphological gradient. So here we try to find the difference between the dilation and erosion operation. Next process which we are going to discuss is top hat. So top hat is something like, it is also called as a white hat. We can reveal some brighter regions on an image in a darker background. So if I have an image with some darker background, on the darker background I have some brighter regions, then the brighter regions can be extracted. So that is what we can do with the help of a top hat or white hat. So here it is performed by applying the difference between the original input image and the opening operation. So it reveals the brighter regions of an image from a darker background. So mostly the other operations, erosion, dilation, opening, closing, morphological gradient, usually it works with some binary images, whereas this top hat and black hat, it works with very well on your grayscale images. Black hat, it is just the opposite operation of revealing the darker region in a brighter background. So here we compute this using the difference between the closing of an input image and the input image itself. So by doing so, we find the darker region in a brighter background in an efficient manner. So now let us do these operations with the help of a code. So here I am going to import a file, sample without noise.jpg file. I am going to read that file and then I am going to convert that color BGR format file into a grayscale image. So let us see how it looks like. So I am going to choose the file. So here I will say sample without noise, open. Then this is the image. Machine learning is the text written on a black background. So here we are going to apply the morphological operations to this image. This is the converted grayscale image. So now first let us apply the erosion operation. So for doing erosion operation, I am going to use a for loop. In that for loop, I define a range 0 to 3. So remember, 3 will not be used in the computation. So we will try to run the I value from 0, 1 and 2. So 3 times we are going to do the erosion operation. So we are going to run cv2.erode function. We give the grayscale image and we are not going to specify any mask here. So it is specified as none, and we are not going to define any structuring element. So by default it will take it as 3 by 3 structuring element. So that is why we define none here. So we can specify our own size of the structuring element, or by default it will take it as 3 by 3 structuring element. So once we erode for the first time, it will show the image. Then for the second time, it will show the image. For the third time, it will show the image. So when I run this, you can see this is the original image. When we erode this image, you can see the line thickness. Let me zoom out this. You can see the line thickness got reduced. The outermost pixel on the text got eroded away. So thereby there is a thinning of the letters in the image. When I do it for the second time, you can see much of the pixels have been eroded, so only few dots we can able to see. So if I do further, we will not be able to see anything. So we have to decide for how many times we have to do this erosion operation, so that I should have the object but the noises should be eroded out. So we should decide based upon our application how many times we have to do the erosion process. Next operation which we will discuss is dilation. So in dilation, again the same logic, only the function will be different. cb2.dilate, I give the grayscale image, and again the structuring element is defined to none, which means by default it will take it as 3 by 3 structuring element, which means 8 neighborhood structuring element, and after doing the dilation process we try to print it and see. So when I run this, we can visualize the result. So this is the original image. Here you can see the outermost pixels have been enhanced from the original image. So you can see a little bit thicker text here. When I do it for the subsequent times, you can see still the text gets thicker and thicker. So there is an increase in size of the object. So you can see further it is getting thicker. So this is your dilation operation. So next we can do opening. So for performing opening, I am going to define different kernel sizes like 3 by 3 neighborhood, 5 by 5 neighborhood, 7 by 7 neighborhood. So here we will try to see the effect of neighborhood on our processing. So we try to take 3 different sizes. So one by one I am going to take the kernel sizes. Using this for loop, one by one I am going to take. When the for loop runs for the first time, it will take 3 by 3. When it runs for the second time, it will take 5 by 5. Third time, it will take 7 by 7. So by taking the kernel size, first thing I am going to do is I am going to create the structuring element using this cv2.get structuring element. So we are going to create a structuring element. What type of structuring element? We are going to create a rectangle type of structuring element. We can also create a circular type of structuring element. For this program, I am going to use a rectangle type of structuring element of size 3 by 3 when the for loop runs for the first time. Second time it will be 5 by 5 rectangular structuring element. Third time it will be 7 by 7 rectangular structuring element. Once my structuring element is defined, I use this structuring element to do the opening operation. So in order to perform opening operation, I give cb2.morphologyX. So I give the image and I say what operation I need to perform. So I am going to perform opening operation by using what structuring element? The structuring element which we defined earlier. So after doing this, I try to plot it and see how it looks like for different kernel sizes. So when I run this section, you can see here, this is the original image. When we apply opening, you can see the spacing between the pixels got increased. So thereby you can see some disjoint nature in the text written. So the spacing between the pixels will get increased. Since it is an opening operation, the spacing between the pixels will get increased. Thereby you can visualize some disjoint in the text. If I increase the kernel size, what happens is, you can see now there are lot of disjoints. So we are not able to visualize the text properly. So it is always better to use a smaller kernel size so that even a small variation can be easily picked up and it can be opened up. In case of 7 by 7, so it becomes almost 0. So it looks something similar to that of your erosion operation. Next operation which we are going to discuss is the opposite of your opening, which is close operation, closing operation. So again we use the same 3 kernel sizes, 3 by 3, 5 by 5 and 7 by 7. So first we get the structuring element, create the structuring element. then use that structuring element to perform the closing operation using cv2.morphology_x. Here we define the flag cv2.morphology_close, which means we will do the closing operation. So closing operation in the sense, now the pixels will come nearer to each other. So or the gap between the pixels will reduce by applying this closing operation. That we can visualize in the result. So when I try to execute and show you the result, you can see this is the original image. Here you can see the gap. Here we can find some small gaps between the pixels. So there are some small discontinuities in the original image. Those things have been removed here. When I increase the size of the kernel, you can see here this section and all, it got closed. So if the small blobs are getting closed, here also you can see, here also you can see in E. So here G, in this, the small regions where small gaps are there, it is getting closed by increasing the kernel size. So if I increase further the kernel size, you can see even the larger gaps are getting closed. So it depends upon our application. So whether I want to close small gaps or I want to close some larger gaps, depending upon which you can select the kernel sizes. Next operation which we are going to discuss is morphological gradient. Again, I am going to apply morphological gradient for 3 different kernel sizes. So first to create a structuring element, then apply the morphological gradient flag. Thereby we perform the morphological gradient, which gives the outline of an object. So when I run this, you can visualize when we apply a small kernel, 3x3 kernel, we can be able to clearly see the outline of the object. Whereas if I increase the kernel size, we will not be able to find the outline, because now the kernel works on a larger region. So in a larger region, it is not able to pick up the outlines. So thereby there is an increase in the text size is visualized. Same way in case of 7x7 also, you can see, since it is working on a larger area, so it is not able to identify the outline, because more number of pixels contribute to that outline computation. So it will result in the increase in the text size of a object. And the last application which we are going to discuss is top hat and black hat. So in order to do that, I am going to take an image, a car image, which has some darker objects on a brighter background and brighter objects on a darker background. So let me load this image, and here I am going to read that image, car.png, convert that image into a grayscale image. Then I am going to define a structuring element, cv2.getStructuring element, and here we are going to define a rectangular structuring element with a kernel size of 13x5. Because here we are essentially going to extract some information from the license plate of a car. So since the license plate of a car is in terms of a rectangular size, I am defining this kernel size in this format, 13,5. Once I define my rectangular kernel or the structuring element, I am going to perform a black hat. So black hat in the sense, we are going to extract the darker region from the brighter background. So for example, in a license plate, if the license plate is white and the text in the license plate is in black color, so we can extract the black regions. The text in the license plate can be extracted using this black hat operation. Next operation which we are going to do is top hat. So top hat is something like we are going to extract the brighter regions from the darker background. For example, if the car is little bit dark color, black color or dark blue color. So in that I have a license plate which is a brighter region. So from a darker background I have a brighter region. So I can extract the license plate as it is using this top hat filter. So in order to do that, we use the cv2.morphologyx. Here I specify the flag cv2.morph_top hat. So then we try to print it and see the black hat operation as well as the top hat operation. So when I run this, let us try to analyze our result. So this is our original image. This is our original image. So here you can see a car with a license plate. So if I see the text on this license plate is darker, which means I can use a black hat to extract this text information from a brighter region, which is license plate. Same way, in the car color is black. From the darker background, I can extract this brighter region, right? So this license plate is brighter. So this I can extract using the white hat. So now let us try to see the result after applying black hat. So here you can see when I apply black hat, the darker region is nothing but our text on this license plate. So that we can able to extract it properly. Here you can see the text on the license plate got extracted because this is on a darker background. The text on a darker background, the text on a brighter background gets extracted in an efficient manner using the black hat operation. When I try to do the white hat operation, you can visualize the entire license plate got extracted properly. Then we can apply some region of interest, masking everything to extract this region alone. Then we can apply some OCR techniques, character recognition techniques to identify what is the number. Then we can do a lot of other application stuffs as well. So the main concept behind your black hat is we can extract the darker region from a brighter background, whereas in white hat or top hat, we can extract the brighter region from the darker background. So in this tutorial, I have discussed about different morphological operations. First we started by discussing on a structuring element. Then we talked about different morphological operations like erosion, dilation, opening, closing, morphological gradient, then white hat or top hat and black hat operation. Thanks for watching. Please subscribe for more technical learning. Thank you.